Logarithms. Logarithms are just a different way of representing exponential equations. So if we have an exponential equation, 5 to the second power equals 25, I can rewrite this using logarithms. So logarithms is just another way to express this exponential relationship. So I would rewrite this equation to its equivalent logarithm expression. So log base 5 of 25 equals 2. This says that 5 to the second power equals 25. So I rewrote the same thing, only using logarithms. Same is true here. 2 to the third power equals 8. This is called the base of my exponential equation right here, and this is also called the base. So log base 2 of 8 is equal to 3. Now notice these logarithms are equal to that power I have up here. Here I have 4 to the x equals 1.6. Log base 4 of 1.6 is equal to x. So logarithms are just a different way of writing exponential equations. So if we look at an exponential equation, here we have y is equal to 3 to the x power. So this is something you've learned about and we've graphed. It's an exponential function. If we want to find the inverse of this exponential function, we're going to replace the x and the y, switch the x and the y, and I have x is equal to 3 to the y power. Well, now how you solve for that is an interesting question. How do you solve for what y is equal to? It's up in that exponent. So to solve for y, we're going to use our newly found way to write exponents. We're going to use logarithms in order to rewrite this as a power equal to something else. And my power here is y. So y is equal to log base 3 of x. So these two are equivalent equations. These are different. They're inverses of each other. So I solved for y, in essence, by just rewriting that as a logarithmic equation. So here, y equals 3 to the x power. And I know my inverse is going to be symmetrical reflected about that line y equals x, because that's my identity function. I could also plug in values up here for y and solve for x, and I would get some values over here. Now notice, when I'm looking at this equation, I look at my exponential equation, y equals 3 to the x. I notice that my values over here are never going to be negative. So I'm never going to get negative values for y here, because even if I plug in a negative exponent, it's just going to make that be a fraction. So I'm never going to have any negative values for y. Consequently, in the logarithmic equation, I'm never going to have any values for x that are negative. So if I'm plugging in values right here, my x is never going to be negative, because even if y is a fraction, my x is still going to be a positive number. So it looks just like this. It's going to get closer and closer to that line, x equals 0, but it's never going to touch. So consequently, if I look at this, I am not going to have any values for x that are ever 0 or a negative number, which is why you can't take the log of a negative number. So looking at this, if I have my function, let's call this first one f of x, which is 3 to the x power, and we'll call my inverse right here, we'll use this one, and I'll call that g of x. So I have f of x and g of x. Now I know, because they're inverses, that f of g of x is going to be x, as well as g of f of x is going to be x. So f of g of x, I'm taking this function and I'm plugging in g of x for x. So I'm plugging in log base 3 of x. So I have 3 to the log base 3 of x right here. And I know that that has to equal x, because they're inverses of each other. So right here I can see if I have those matching bases, it's just going to undo each other and give me that value of whatever I'm taking the log of. Same is true with g of f of x. I take g of x, I take that x, and I'm going to replace it with f of x. So I have the log base 3 of 3x, and I know that's also going to give me x. So notice I've got the bases matching here in a logarithmic equation, and it's whatever power that second one is that I'm taking the value of. So in this case, it's going to be x. If this were a different value, it would be whatever I have, whatever that power is, as long as those bases are matching. So let's look at some examples of just working with logarithms and getting a little bit more comfortable. So here I have log base 9 of x is equal to 3/2. Well, that's a fraction. Remember, when I have a logarithm and it's equal to something, this is going to be my power. So I have 9 to the 3/2 power equaling x. When I have a 3/2 power, that means I'm cubing it and taking the square root, or the 1/2 power. So I have the square root to the 3rd power. That's the same as 9 to the 3/2. So this square root just represents my 1/2. So if I have 9 to the 1/2 to the 3rd power, that's the same as the 3/2. I can go ahead and take the square root of 9, which is just 3, and then I can cube it. So it's going to give me 27. Now that's nice because it has an equal sign, but oftentimes you'll get logarithms that look like this. And you have to remember the exponential form. 3 to what power gives me 1/27th. So sometimes I write an equal sign and a question mark. You can write an x, but sometimes there'll be an x in the part that you're evaluating, and you don't want to confuse the x with that. But you can write an x. I've seen people do that before. So then just rewriting an exponential form, 3 to the question mark equals 1/27th. Now I can rewrite this as the same base, because I know if my base is the same, then I can set my exponents, or my powers, equal to each other. So here I have 3 to the question mark, written from here, equals 1/27, which is 1/3 cubed. 1/3 cubed is the same as 3 to the -3rd power. So I know my question mark has got to be -3. So log base 3 of 1/27 is equal to -3. Here, I'm also going to do the same thing. Equals question mark. Now, as you get better at this, you'll be able to recognize 16 to what power gives me 4, and you won't have to go through this translation process to the exponential equation. But it's helpful until you get a good idea of how to do it. So I have 16 to some power is equal to 4. Well, 16 is bigger than 4. So I know this is probably going to be some sort of fractional power. So I have 4 squared, which is the same, because I get my base the same as 4. 4 squared to the question mark is equal to 4 to the 1st. And I just put this 1 here so you could see what you're comparing. So I know 2 times this question mark has got to give me a 1. And then dividing both sides by 2, my question mark has to be 1/2. So log base 16 of 4 equals 1/2. 16 to the 1/2 power, or square root, gives me 4. So that's just rewriting an exponential form as you're translating logarithms, just to kind of see what's going on. So let's just practice a little bit rewriting in logarithmic form or an exponential form. So here I have 4 to the -2 equals 1/16, and you can go ahead and check that. I just have 1/4 squared, which is 1/16. And rewriting in logarithmic form, this base is going to be the base of my logarithm. Log base 4 of 1/16 is going to equal my power, in this case -2. So you should be able to go back and forth between these two forms. 8 to the 2/3 equals 4. Log base 8 of 4 gives me that power, 2/3. So being able to go back and forth here. And this 2/3 power is the cubed root of 8 squared. So the cubed root of 8 is 2. 2 squared gives me 4. Here, a little bit more generic. So I have log base a of a is equal to 1. Translating this into exponents. So notice my base is matching what I'm taking the log of right there. A to the 1st power is equal to a, and that's always true. So if a happens to be 3 or 4 or 5 or 10, if this matches this, I'm going to get a 1, because whatever this is to the 1st power is going to get me back to that original 1. Here's another one that's pretty common. Log base a of 1 is equal to 0. A to the 0 power is equal to 1. It doesn't matter what a is. It's going to give me a 1. 5 to the 0 power, anything to the 0 power is going to give me a 1. So anytime you have a log, no matter what the base of 1, you're going to get a 0. And if you don't remember it, just go ahead and write it in exponential form. So here I have a couple more examples. This one, log base 7 of 7 to the x minus 5. So here, if you remember, I'm taking a log with a base to this same thing. So I'm taking that to a power. It's undoing itself. So I know it's going to be x minus 5 from what we learned before, but let's go ahead and look at this. Let's say we didn't know. If we rewrite this in exponential form, I have 7 to the question mark is equal to 7 to the x minus 5. So my base to some power is equal to what I'm taking the log of, this 7 to the x minus 5. Well, now I have the same base, and I can see that this has got to be x minus 5. So the answer to this, and it's not really an answer, you're really just simplifying it, is x minus 5. Simple form of this is just whatever that power is. Same is true here. I have an exponential function. I have something to a power, but those bases match. So if we look at what we looked at before, I know it's going to be 2x plus 5. But let's go ahead and look at it. Let's rewrite it in logarithmic form. So I'm writing this exponent, even though it's got a log here, I'm thinking of this as just a power. And you could think of it as one big A, 6 to the A power. So then I would rewrite it in logarithmic form, doing log base 6 of question mark. I've got this question mark right here. I don't know what it equals. Of question mark is equal to the power. And this is the power. The power is a logarithm in this case. Log base 6 of 2x plus 5. Now these are the same. So it's got logarithm of the same base, which means whatever you're taking the log of here has to equal this. So my question mark must be equal to 2x plus 5. And so that's just proving it in a different way. Here, looking at these logs, I don't actually have to have that 10 there. If there's nothing there, it's assumed that it's going to be a 10. That's a common logarithm. So I have log base 10 of t is equal to log base 10 of t squared minus 6. Well, they have the same base. And so whatever I'm taking the log of has to be equal. T has got to equal t squared minus 6. I know that has to be true because of the property of equality of logs. So here I have t is equal to t squared minus 6. And then this is a quadratic. And anytime you see a quadratic, probably the easiest way to solve a quadratic is to set it equal to 0. You don't have to, but it's a common way to solve it because if you can factor, setting it equal to 0, you can use the zero product property rule. So subtracting a t from both sides, and I have t squared minus t minus 6 is equal to 0. And then I can go ahead and factor it. That's t minus 3 times the quantity t plus 2. And then solving for 0, setting this equal to 0 and this equal to 0, I get t is equal to 3, but I also get t is equal to negative 2. Now here you have to remember what you're doing because you can't take the log of a negative number. If I were to substitute this back up here, I would have log base 10 of negative 2. Now if you remember the graph of the logarithm, you know that you're never going to have a value that's negative. And so this one I have to discount, and my answer is merely t is equal to 3.